Say you're hunting for one name in a 1,000-page phone book. Flipping through it page by page could take all day. So don't. Open straight to the middle and ask, is your name before this page or after it? If it's after, rip out everything before it. 500 pages gone in one move. Then open the middle of what's left and rip away half again and again. About 10 rips and the single page is left. That's your name out of 1,000. Let's see the same trick as a quick game. I'm thinking of a number, 1 to 16. I'll only say higher or lower. Let's start right in the middle. Is it 8? Go higher. Okay, so the number is bigger than 8, which means 1 through 8 are impossible. We can throw them all away. Look what happened. In a single guess, half the numbers are gone. Now we just do it again with what remains. 9 to 16. The middle is now 12. Higher or lower? Go higher again. So 9, 10, 11 and 12 are out too. Only 4 numbers are left. We guess the middle. 14. This time go lower. So 14, 15 and 16 are gone. And the only number left is 13. Just 4 guesses to find one number out of 16. Because every guess threw away half of what was left. Did you notice what just happened? You just ran binary search yourself. It's how you find anything in a sorted list, incredibly fast. But there's a catch. A very important catch. Binary search only works when the data is sorted. Let's understand why. Back in the game, you guessed 8 and heard higher, so you threw away everything below 8. That only works because in sorted data, smaller values are guaranteed to be on one side. Without sorting, that guarantee disappears, and the entire algorithm falls apart. Consider this array: 8, 2, 15, 1, 10, 20, 4. Notice that it's not sorted. Suppose we're looking for 10. The middle value happens to be 1. I tell you the target is higher. Can you safely ignore half the array? No, because larger numbers exist on both sides. The information higher is no longer useful. Binary search depends completely on order. No sorting, no binary search. Always remember that. Now let's transform the idea into an actual algorithm. We'll keep track of 2 positions, low and high. Low represents the beginning of our search range. High represents the end. Initially, low points to the first element and high points to the last element. Everything we need to search is between those 2 positions. Next, we calculate the middle position. Once we have the middle, we ask 3 questions. Question 1. Is the middle value equal to the target? If yes, we're done. Question 2. Is the target larger than the middle value? If yes, search the right half. Question 3. Is the target smaller than the middle value? If yes, search the left half. And then we repeat the process. Again and again and again. Until we find the target or run out of elements. Here's the complete Java implementation of binary search. Don't worry if the code looks big right now. Let's run it step by step on a real example. We're searching for 71 in this sorted array. First, low starts at the beginning of the array and high starts at the end. Now we need to find the middle position. You might have seen some people calculate it like this: low plus high divided by 2. But in real applications, low and high can become very large numbers. Adding them together may cause something called integer overflow. That's why we use low plus high minus low divided by 2. It gives us the same middle position, but it's safer. For our current range, the middle value is 42. Now we compare 42 with our target 71. Since 71 is larger, we know the answer cannot be on the left side. So we move low just after the middle position. The search range becomes smaller. Again, we calculate the middle. This time the middle value is 63. We compare it with 71. The target is still larger, so we move low forward once more. Now only a small portion of the array is left to search. We calculate the middle again. This time, the middle value is 71. It matches our target exactly. The condition becomes true, and the function immediately returns the index. Notice what happened here. We never checked every element one by one. At each step, binary search removed half of the remaining search space. And that's what makes it so fast. And this isn't just a Java thing. The exact same logic works in any language. Here it is in C++. And here it is in C. Every iteration removes half of the remaining elements. That means the amount of work grows very slowly. In computer science, we describe binary search with O log n. Read as log n.
Don't worry about the math for now. Just remember the idea. When the data doubles, binary search adds only one extra step. That's incredibly efficient. Let's summarize everything. Binary search works by repeatedly cutting the search space in half. It requires sorted data. It uses 3 simple decisions: found it, go left, or go right. Its time complexity is O log n, which makes it dramatically faster than linear search. That's binary search, one of the simplest and most powerful algorithms you'll ever learn.